All right, chemistry folks, welcome back to our lecture cycle here. We are going to focus in this unit 8, on chemical reactions. Cool thing about this unit is we get to do some laboratory work again, actually quite a bit. Do some cool demonstrations and stuff like that. But we need to build some fundamentals first. First things first. And so first of all, I feel like you probably learned this at some point in your science careers, but chemical reactions are often written with a little arrow, right? That little arrow means yield, by the way. And then our reactants, which is our starting materials, are written on the left side of that arrow, and our products are written on the right side of the arrow. So a good example there, let's say we had some magnesium metal, and we put that into some hydrochloric acid, right? We would see some evidence of a reaction. In this case, we'd see some bubble formation, because of that hydrogen gas, and then a new compound would form as magnesium chloride. Now, at this point in our learning cycle, this little 2 right here that I used for balancing the equation is not necessary. We are going to get there. That's going to be something we do on our tests and quiz at the end of the unit. For right now, we don't have to worry about balancing, okay? So we can just write out what we call a skeleton equation, which just shows the reactants and products with the correct formula, but doesn't worry about going back and balancing things yet, okay? Now, in class today, you should have gotten a little cutout of reaction symbols, right? This got tells you what the little triangle means, what the arrow means, or the double arrow means, stuff like that. That's just stuff that's a resource you can use. You can tape that to your periodic table so that it folds out wherever you want to keep that, or if you just want to remember what the symbols mean. It's just a resource for you guys, okay? I am going to expect you to be able to at least use that resource or know what they mean. Either way, you can use it on tests and quizzes. I don't really care. It's just something I want you to be able to have at your fingertips, okay? So make sure you've got that ready to go if you don't know what those symbols mean already, because they will come up. So one of the things you're going to be asked to do is convert chemical reactions in word form from word form to your equation form, okay? And what that entails mostly is, sorry about that. Mostly what that entails is the ability to write formulas, right? So if I write out the whole reaction for you, in this, like I did in this case, you need to be able to then look at the name of the compounds and write their appropriate formula with the appropriate symbols, okay? And one of the things we'll learn to do is predict products anyways, but for now, we want to be able to write this out. So what steps can you use to correctly write the equation? And again, we're not worried about balancing just yet. All right? So what we have here is compounds that we're starting with. So my reactants, solid sodium carbonate. So that's Na. So sodium is Na plus. Carbonate is the CO3 2 minus. Right? So one of my reactants is sodium carbonate. So I got a +1 and a -2. So my formula there would be Na2CO3. Reacts with, so that's indicated by that plus there, aqueous hydrogen chloride, which we would call hydrochloric acid. So this is H plus Cl minus, one of each. So this is HCl. Okay, to produce or yielding sodium chloride. So Na plus Cl minus, so that's NaCl, and carbon dioxide. So the di there, this is a molecular compound, CO2, and water. And we should all know the formula for water is H2O. Okay? So what we're doing is we're taking skills we learned in our chemical names and formulas that I said over and over again. This is not going away. You have to remember how to do this. We're taking those skills and now applying them to what we've learned, what we're learning about the way reactions are written. Okay? So we have our reactants on the left side, sodium carbonate and hydrogen chloride or hydrochloric acid. Produces or yields, that's a synonym for yields, sodium chloride. That's an ionic compound, so we have to balance our charge, one of each. carbon dioxide, molecular compounds, so we just use the name to write our formula, and then of course water is H2O, and that's how we'd write that. Now, that's not a balanced equation, but again, we will worry about the whole balancing process later. For now, I want us just to be able to understand that this skill of using names and then writing their correct formulas is going to be an important piece. Okay. Now, oops, sorry about that. Our next step then, formula. My computer is being a little stubborn for me here. So, next thing is we want to be able to predict products. Okay, when we know what the reactants are. Okay, and again, that entails some knowledge of the way chemical formulas work. Okay, so in the case of this, zinc and hydrochloric acid. Zinc is a metal, right? So it's Zn2 plus H plus Cl minus, right? Now notice that I am writing those there because that helps me predict what might combine with what on my product side. So these are my reactants, zinc and hydrochloric acid. Now, if a reaction were to take place, that means I would have to be doing some reconfiguring of what I started with, right? If I ended up with zinc and HCl on the other side, there'd be no reaction. All right, so zinc, in this case, is going to have to combine with something, and I'm going to have to split this HCl apart, okay? And so we need to use then the charges of our elements to figure out what becomes what. Okay? So, one of the things we learned back in our unit on ionic bonding is that a plus always combines with a minus, right? So the only option here is for zinc to combine with chlorine, right? And essentially zinc is replacing that hydrogen atom in that compound. So zinc's a plus, metal, it's always going to combine with a nonmetal. So my new formula over here is going to be ZnCl2 plus hydrogen gas. Now, why did I put the 2's there? First of all, the 2 is there because hydrogen is one of our Brinkelhoff elements. The 2 is here is because I need to write the correct formula based on the rules we learned last semester for ionic compounds. Zinc's a plus 2, chlorine's a minus 1, therefore crisscross method, I get ZnCl2, not just ZnCl. Alright? So, again, we're taking the stuff we learned about names and formulas. All that information is still true, and we have to apply it to what we're doing here. So, next one, so this is called a single replacement reaction, by the way. This one's called a double replacement, and we'll go about how you can tell that here in just a minute. So, what I have is aluminum, oops, sorry about that, Al3 plus, and sulfur, and sodium, and oxygen. Okay, so again, the reason I'm writing those formulas, or the charges up there, is so I can make a prediction about what might combine with what. So again, if a reaction were to take place, that means I'm going to have to split these guys apart, all right, and recombine them in a new form. So if a reaction takes place, that means my aluminum, if it's no longer with sulfur, it's going to have to combine with another negative element, so that would have to be oxygen. So Al2O3, and sodium being a plus would have to combine with sulfur to make Na2S. All right. Now, again, not worrying about balancing, but the logic I'm applying here is a plus needs to go with a minus. And if a reaction is to take place, that means that I have to recombine, take things apart, and recombine them in a different form. All right, so that's what's called a double replacement reaction. Now, in this case, you notice the little triangle there. So that little sheet I gave you guys in class today tells me that that's heat, right? So this is what we call a decomposition reaction, right? So in a decomposition reaction, we're taking a single material and splitting it apart into its smaller materials, okay? So in the case of mercury oxide here, I'm actually going to separate the mercury from the oxygen, okay? So in this case, I'm going to create mercury and oxygen gas. And again, why do I need that 2 there with the oxygen? it is one of those Brinkelhoff elements. All right. Next one, we've got iron and oxygen gas, and this is what we call a combination or a synthesis reaction. All right. So notice the Roman numeral 3 there. Iron's a transition metal, so I indicated the charge of this particular type of iron as a +3, and oxygen gas. So if they are to react, in this case, this is what we call a synthesis reaction, in which case we're taking the iron and the oxygen and combining them, okay, using the correct formula. So this is a +3 minus 2, right? So this is going to be Fe2O3. It's going to be my product on the other side. And the next one, okay, we are going to learn to recognize this type of reaction as a combustion reaction. That obnoxious bell. Okay, so in a combustion reaction, so whenever we're taking a hydrocarbon, so a hydrocarbon is what we call any sort of carbon linked with hydrogen, right? In this case, that would be butane. But in this case, what we get as a product of our hydrocarbon combustion, all right, and this is simplifying it a little bit, but the generic formula, right, for combustion of a hydrocarbon, so we know it's combustion because we're combining it with oxygen, and notice we have a little heat symbol there, fire triangle, fuel, check, oxygen, check, spark, check, right? So we get a combustion reaction, and when we do that, our two products are always going to be carbon dioxide and water. Now, does everything we burn produce carbon dioxide and water? Not necessarily. Sometimes we get some impurities or incomplete combustion, but we're going to simplify this and not worry about a low oxygen environment giving us carbon monoxide instead of carbon dioxide and nitrogen oxides that can form as a result. Okay, we're going to keep it simple. Hydrocarbon plus oxygen. That is your immediate indicator that's going to be a combustion reaction. And when we're combusting a hydrocarbon, we get CO2 and water every time on the right-hand side. Okay? Now, last but not least, single replacement, double replacement, combination synthesis, decomposition, and combustion reactions. We need to learn how to recognize these when we see them. So a basic formula, right, for a single replacement reaction. I have one element by itself and another compound. So a single element reacts with a compound. And in that reaction, right, one replaces the other one. So in this case, I can replace B with A, right? And so I can get AC plus B. All right? So single replacement is where a single element replaces another element as part of a compound. Okay? In a double replacement, we have two compounds. Okay? And essentially, the two cations, or you could say the two anions, replace each other. So in this case, I would get CB plus AD. Right? Now, in a combination or synthesis reaction, I'm taking two individual pieces and putting them together. So I'd be taking like element A and element B and creating a compound out of it. Decomposition is essentially the opposite. I have a compound and I split it up. And then a combustion is a hydrocarbon, and oxygen gas yields CO2 and water. Okay? Now, again, this is a simplification of the combustion process, but for CP chemistry and the basis of what we're going to do, this is fine. So the CnH2n plus 2 is just the formula we use for figuring out our hydrocarbons. That's not so important right now. We just have to remember, for us, in Mr. Hudeberg's CP chemistry class, a combustion reaction is going to be a hydrocarbon plus oxygen, and of course a little spark there to complete the fire triangle, right? Produces CO2 and water. So my products of hydrocarbon combustion are always going to be CO2 and water. All right, that concludes this lecture. All right, you're going to use these notes for an entry task tomorrow, so we'll have them ready to go. Peace.